Today in calculus, we will be talking about velocity and rates of change. Say that you have the equation for the position of a particle. The velocity would be the derivative, otherwise known as the instantaneous rate of change, otherwise known as the slope, of that position equation. And the acceleration is the second derivative of the position graph, and it is the derivative of the velocity graph. Done. Here we have the graph of a velocity equation, and we're trying to figure out when it reverses directions. Well, when the velocity is 0, it reverses directions. Because it crosses the x-axis and changes sign at 2 and 7, that is where it reverses direction. Now we're going to try to find when the body is moving at a constant speed. Well, when the slope of the velocity graph is 0, then it is moving at a constant speed, because then the acceleration is 0, since acceleration is the first derivative of the velocity graph. As you can see here, the particle is moving at a constant speed from 3 to 6, except that isn't how you write it. That isn't how you write it either. That is the correct notation. Now we're going to find the speed of the particle from 0 to 10 seconds. Graph-wise, all that means is that you flip all the parts below the x-axis up above the x-axis. Essentially, the reason that you do this is because speed is the absolute value of velocity. Next, we're going to graph the acceleration where it is defined. This is not actually that hard. Basically, acceleration is the derivative of the velocity function. So all you do is graph the slopes of the velocity to get the acceleration. Okay, the graph was the easy part. Now we're going to transition to particle motion. So, say we've got this particle, and he is moving along a line so that his position is given by the equation t squared minus 3t plus 2. With that equation, we're going to try to find the displacement during the first 5 seconds. We're going to take the displacement at 5 and subtract the displacement at 0 from it, and when we do that, we're going to get that the displacement is 10 meters. Now, we're going to find the average velocity during the first 5 seconds. To find the average velocity, you take the distance over the time. We've already found that the distance in the first 5 seconds is 10 meters, so you divide that by 5 seconds and get 2 meters a second. Just make sure your units are correct. Say you have the position equation t squared minus 3t plus 2, and you're trying to find the instantaneous velocity at 4. Well, velocity is the derivative of the position graph, so you take the derivative of the position equation, and you get 2t minus 3. To get the instantaneous velocity, you plug in 4 for t, and end up getting 5 meters per second. Okay, now we're finding the acceleration of the particle when t is 4. We already know that acceleration is the derivative of the velocity and the second derivative of the position. So, the derivative of the velocity equation, which is 2t minus 3, is 2. So, the acceleration is 2 meters a second for the entire equation. Almost done. We're going to find the value for t for which the particle changes direction. We know that it changes direction when the velocity is 0, so all you do is plug in 0 for the velocity, and then when you do the math, you get that it changes direction at t equals 3/2 of a second. For the last part, we're going to find out when s is at a minimum. We know that s is at a minimum when the particle changes direction, and we know it changes direction at 3/2 of a second. So, plug in 3/2 for t, and you find that it changes at a 4th.